Just a sec. Range.
Hi.
Hallo.
Hallo.
Do you hear me?
Yes.
Awesome. Now we made it. Sorry, I'm in the car right now, so I hope it works. Not driving myself, so how are you guys doing?
Cool time.
Looks good. Nice weather.
Oh,
You should have like a floating device with your laptop.
Now I'm joining with the phone.
Yeah. Great. So let's still wait a little. So what did you do last time? Should we like continue on that, or what would you like to do? And I also see we have new members, right? So whoever hasn't or wants to tell something about himself, herself, feel free. Oh, yeah. Come on, I don't know. You've been there?
Hello, I am Conrad, yes.
Awesome. Did you already like tell something about yourself? I wasn't there last time, so.
No, this is first time I'm here.
Awesome.
Thank you for accepting my invitation, accepting my request last day. After I attend last 2 days and your live demo, according to I am into learning OpenUSD because this is related to my PhD study. I'm really interested to attend your weekly meeting, weekly study in OpenUSD study group. This is my great contribution for your study pathway.
Yeah, thank you for joining. That's great.
Thank you.
May I ask the field you're in with your PhD?
Sorry, could you please repeat again?
Like, what field are you in?
Okay,
What are
sure.
you doing your PhD with, roughly?
My field is electrical and computer engineering, but I more focused on 3D reconstruction and post 3D reconstruction, the combination between physical AI and agentic AI. More specifically, I worked on NVIDIA Omniverse, NVIDIA NeoRec, and NVIDIA Isaac.
Okay,
Nice.
interesting. Yeah.
And if you're experienced with NVIDIA NeoRec, for example, you could also like show a little something next time if you like. What do you?
Not yet, because at the moment I am working on 3D reconstruction based on some recent publication like VGT Omega or VGT T3 based on the NVIDIA last research. And after I make reconstruction, I may provide NVIDIA NeoRec to photorealistic reconstruction and visualize inside the NeoRec. And after of NeoRec, maybe I may use NVIDIA Isaac Sim in order to visualize in that environment.
Yeah, that's cool. Yeah, especially with Gaussian splatting support. Did anyone already try the Gaussian splatting in Isaac Sim? Andy, I think you, right? You're muted.
I'm just starting with a 360 degree camera drone, a new DJI avatar. So I'm new in the workflow, but I did get some results. But it's experimental workflow right now. Yeah, there are not in the commercial fields. There are other classes of drones from factories like they use 360 cameras in a professional space. There is a complete software workflow for Gaussian splats. I'm experimenting some tools.
Very interesting. No? And also read, like there, yeah.
The camera, the commercial drone system is the anti-gravity A1 with someone, and they have a workflow for complete for Gaussian split results. Amazing results.
Awesome. Yeah. Do you know how much it costs?
The waiter is about this DJI is not a commercial. Is about €1,400. There are different configurations for remote, and you can also control this drone without a classical RC with manual controller like like a toy. Incredible is and the anti-gravity is about $50,000, I think. The drone.
Oh, yeah. Cool. If you have a link, or you might want to post it. I've posted just pasted a link to our session with NVIDIA last, which we did on Monday, right?
Yeah.
No, when was it?
Yesterday.
Yeah. Oh yeah. Yeah, time flies. Yeah, all right. So whatever. There are always like interesting links, and I can quickly share my screen as well.
Yeah.
Because I showed like how to use a Claude code and then the OVRTX library and the skills within to create like an MCP server, so a kind of agent helper. I hope it works. Do you see it?
Not yet.
It might be a little too slow. Maybe let's still wait a little. Now, do you see it?
Nope, still a white screen on my end.
Oh man, that's so internet kind of sucks. Well, yeah, I've posted the link. It's like on the like after 1 hour approximately. We show basically how you can use an agent to create an MCP server, which helps you in this case to create a 2D rendering of a 3D object. And
Yes. Now.
now you see it. Yeah. So here is like a little excerpt of this. So everything is like contained in the OVRTX library itself with the repository, you know.
Mm-hmm.
And this is really really useful.
Yeah, I thought my thought yesterday.
Yeah. And so it was like a matter of an hour, and we created it created like with Claude Code this helper. It's used with Claude Desktop in this case. And as you see, like you can easily create like these 2D. It's maybe hard to see. It's a 2D top view rendering of this 3D drum, and it's like totally supported by the agent, and that's really neat. But yeah, you can have a look yourself. I can quickly show you the source as well.
I posted
So
a link
it's
in the
that's
chat.
good.
What is possible
Great.
with
Awesome.
Gaussian spreading with 360 cameras. It's amazing.
Yeah. That's good. That's good. So this is the source code of the OVRTX, right? And it has these skills, and this is really interesting. It tells basically your coding agent the specifics of programming with certain USD aspects, or also aspects in the let's open, for example, this in some I have to activate my power. Just a sec. Oh, it should work again. Yeah, now I've got power again. Just a sec, it's coming. Yeah, do you see it? I'm just in the Autobahn in Austria, so this is a little traffic here. As you see here, it's the agent reads this, right, and it says, okay, if you want to use this, you have to like do these steps basically, right? And that's basically also for you to read and to get some info about that. but also for Cloud Code, for example, for the agent. And it's really, yeah, it works quite well. So that was what I wanted to share with you. If there's something else related to agents, or you want to add, you could also look into that a little, or continue with our book. What's your feeling? So maybe also worth looking. Also, what I here saw was really nice use case using with Paul Katzinger. He also joined the call, and he showed an integration of Nemo Claw with Omniverse. Where is it? It's about here, yeah. So he had like a Nemo Claw connected to a Telegram bot. So he talks using Telegram to the Nemo Claw agent, and he sends like on site 2 pictures, right? And says, give me like a 3D model out of these pictures, right? And Nemo Claw then calls an MCP of image to 3D and creates like a 3D model, and then integrates everything into the digital twin, for example. So I think this is the future of human-computer interaction. I'd say, from my point of view. So we'll more interact with agents like that. But yeah, I don't know what's your point of it. But yeah, if you have any any questions or anything we should cover.
Can I make one comment for last presentation regarding to Nemo Claw Isaacson? This is very great. I attend last 2 months in Edmar online webinar, and one of the interesting in this field implement Nemo Reconstruct, and this is and I can share the link here.
Yeah, that would be great if you could post the link.
And they upload. We can upload the real environment by our phone, and upload the phone on the UI, the developer design, and this is directly connect to Nemo Claw. And Nemo Claw, as you know, this is the open shell, the sandbox. And after we upload our environments, the OpenClaw and the Nemo Claw can make a 3D reconstruction based on the engine of the NVIDIA, for example, 3D Gaussian, the platform. And after that, you provide a PLI format. You can make NVIDIA new rack in order to making the photorealistic of the 3D environment. And in the last time, you can import the on the NVIDIA Isaacson. This is the a bit similar to the work you showed me, but your work is better, makes sense. Why? Because in your work, which I saw last day, you work on MCP server, and the MCP server, the MCP tools, is a bit more better than the latest work. Why? Because the MCP server can use some tools. This is better.
I also think the future is basically with MCP servers interacting with the agents. I've also made a. I can quickly show you the slide on that. So I showed yesterday. Maybe it's interesting for you as well. So right now we're using expert tools, right, to create OpenUSD environments. But in the future, we will have a lot of agents and agents talking to MCP servers, right? Yeah,
Yes, exactly. Yes.
Yeah. So yeah. So yeah, and this creates then the digital twin pipeline, an agentic one. So that's kind of a little my vision, yeah, for that. Yeah, but maybe let's then continue with the book, right? If or any other comments to new reg. Just a sec, I have to help my daughter who's driving. We're crossing a traffic accident, so just a second. Okay, we made it. So yeah. Then I think let's go through the day 2 of the book, if you guys like. What's yeah. So we already covered creating the OpenUSD scene, manipulating content, and I think we did like did we do this transforming? No, we didn't do it. That about transforms. Yeah, it's also basic, but still, yeah, worth it, I'd say. Manipulating X forms, understanding the math. Well, yeah, I mean, yeah, we all have a common basic knowledge of math, so I think, yeah. So essential skills need to control the elements. Yeah, self-driving candidates and position and relative objects. I won't read that. Yeah. X forms, yeah, fundamental building blocks of OpenUSD scenes. That's really important, right? Yeah, basically, this is how you define transforms, right? Yeah. Relational knowledge, that is a starting point. Ease of use. Create a prim, defining its path, just referring to the type name, program ends, we can create prim. Yeah, well, that's basic, creating a prim, right? So yeah, if you have followed the USD study learning path, this should be all clear. I wouldn't go too deep on that. I mean, you create a prim like this, you give it a name and a type, right? What happens? Create prim. It's called this. It's as a stage-defined prim with a prim path. That's this world X form, and the prim type X form. It's yeah, basically creating a transform. So yeah, and here we have a different type, right? It's creating a distant light in this path, but basically a light is also a prim. And then, yeah, okay, so we want to transform the light as well. So we want to move it. And so we add a transformable schema basically to the light prim, to the, yeah. So we say, okay, we want to transform this by writing that, right? And then we can say, okay, now add a rotation operation to our prim, and it's gonna be rotated, right? Rotate X, Y, Z up. It means first rotate around X, then around Y axis, and then around Z axis, right? That's what it says here. And so, yeah, then we rotate our lights around the axis, you know. And depending on on our up axis, that would be like probably the Z up or Y up, you know, depending where it lights shines. Yeah, transform order is a very important topic because you get distracted easily, or like get the wrong order, and you wonder why objects aren't showing up the way they are intended. We're referring to the combination of translation, rotation, and scale, right? And it depends. Yeah, what the sequence depends. It will be probably explained later. Transform cumulative, exactly. Each transform builds upon the previous one. So the order of application determines the final transformation. Exactly. Especially, for example, if you think about, I think that's also what they show here. Yeah. So yeah, that's it matters if you first translate and then rotate, or first rotate and then translate, right? So here is an example, right? In the one case, the cube is like rotated and then translated, and in the other way around, and the result is completely different, right? So yeah, and you're very flexible of applying different rotations, you know. In USD, you can do it in any order you like, but there is like a standard order when applying these transformations. And this is also an important statement: clear X form up order. That clears every transformation step. So that's always something you should do first, in order to be sure that you get the transformation as intended, right? So here we're using different translation, then an orientation, and then a scale up. Define the order. Yeah. Check the transform order of our X form using it. Yeah, you always can also query these operations as well. And that's also with this X form get order X form ops. You know, and it prints basically the name. What's that? Well, yeah, we can then set also values to the operations as well. Yeah, we should do the like an example as well. You know. That's basically just adding some orders, some scale, some transform operations, set some values, and then you get like these different transformed elements. Yeah, there are multiple ways to represent rotations. A lot of, for example, Euler angles. That's rotating around an angle to, in a certain sequence of the axis, right? Or quaternions. are also a safer way to describe rotations. But yeah, basically, you can use what you want, basically. Yeah. So mastering rotation. Okay, so now they're basically discussing the different rotation types. As I said, Euler angles. And yeah, the axis and 3D space, right? Yeah, that's what I was talking about. There are certain situations where Euler angles don't work because there is something as a gimbal lock, right? Some angles get too close to each other, and then the math gets confused. Has anybody experienced like the gimbal lock thing as well with Euler angles? The 3D guys maybe?
No.
Yeah, you might come over it, especially if you transform rotations into each other. Yeah, basically that's a good thing to see draw the pitch roll, and you rotate the object around these axes. And quaternions, yeah, that's another mathematical concept of which we can use to describe rotations, and they are better, especially if you calculate a lot with rotations, because they don't have this gimbal lock.
Ambition is the type of car that you keep.
Yeah, there's a question. No. But that's the art. Yeah, if you like math, you can go into that, and you can basically calculate one into each other as well. And the main thing of describing transformations is using matrices, right? And so here they discuss the different components of a matrix, like what contains the translation part, the scaling is here, right? And the rotation matrix is this. And this basically describes a transformation of an object. Or yeah, maybe you could also say it transforms the coordinate system of this object, right? It's like that. Yeah. You can read it by yourself. They explain each component and go into detail. It's worth reading if you're dealing with 3D computer graphics. This is something you always get in touch with. Yeah, Euler angles, quaternion rotation, rotation matrix. These are like the three ways of describing transformations. They discuss here the pros and cons. That's good. Yeah, playing with scene layouts. What's here? Staging multiple objects. Yeah, sure. I mean, that's the nature of scene layout, that you transform, you bring in objects into the scene and then you transform them. Right? And yeah, that's also transforming like hierarchically. So a car in the garage, right? If you move the garage, then the car in the garage is moved as well. And that's basically combining the transformations of the garage with the transformation of the car. Right? It's always, I don't know if you have come across this, if you're working with a simulation, with physics simulation or Isaac Sim, you always have to think about how do I put the things in my scene? Do I put them like into a hierarchy or into a flat list? Because do they have to be transformed independently of each other if you throw things around, right? That's something you have to keep in mind. And obtaining world and local transforms, you can basically get the local transformation, or the global transformation is every transformation of the element apply. So the car in the garage, right? If the garage is on the in Ulm, in my hometown, the global position, it's like in Ulm of the car, right? If it's in the center of the garage, right? If the garage is in Stuttgart or wherever you are, sure, the global position changes, right? It's like something in a box, it just moves. Great. Yeah, here's there is a built-in method to calculate the world transform. It's called compute local to world transform. It's a built-in method of this transformable class. Here is the same for the local transformation. So here you would get only the transformation of the car inside the garage, right? And with this compute local to world transform, you get the world position. Timecode also, I mean, the car can move, right? So you have to specify a timecode at which point in time you want to get the transformation. And there are extract for each components also methods to do that. This is script. I don't know if I can actually start the script. We should try this a little. Maybe let's go to the bounding box as well. Or any questions about the transformation yet? It's not. Well, let's go ahead and do the compute the bounding box. We want to know how large the object is, and this is something also I used for the top view rendering. If you remember, I calculated the bounding box of the element and then rendered it just like this portion. That's basically the bounding box of this element, right? And you compute it like this. There is a B box cache, and you say compute world bound. We'll do an example, I'd say. But just that you have heard it. It's bounding boxes always have a minimum and a maximum point, and the actual bounding box is in this case, let's see, aligned range. That would be like transformed to the transformation, but world bound. It's basically a box around the object. Let's explore the advanced methods for manipulating S forms, and let's apply these things. Now we get to the example. Let's set a stage with 3 dice, allowing us to reinforce our understanding of fundamental transformations. That's good. This focus will deepen our understanding of how transforms affect the composition behavior of objects within a stage. The 9 shows the type of dice we will use for example stage. Okay. Yeah, we have to download the folders and assets. We did that already last time. If you haven't, now would be a good point in time to do it. I just posted to the link. Where is it? There it is. Yeah, let's start creating a new stage called dice scene, importing some packages and referencing the dice as an external reference. This is the dice, right? Remember to consider the directory structure and set your working order to the folder where you want the dice scene to be created and saved, and where you wish to reference assets from the asset folders, just like we did with the status scene in chapter 4. Okay. So what do we have to do here? We create a new scene. We define like a transform node, right? Dice 1, and we add a reference to this dice asset, right? So yeah, let's do that, and then we transform it. So this should be also known if you have done the USD learning path, adding references, right? This transforms the scene. It adds the translation, rotation, and scale. Scale is 1, 1, 1, 1, so we won't see any scale, right? Dice in the scene, it gives a reference point from a dice, which is dice on the transformation relative. Okay, so we add another dice 2. Add an okay. So we reference basically the first dice using this, right? Add internal reference in our dice 2. That's also a quite common pattern. You have some, and we also read this in the USD study journey about like instancing and referencing. Yeah. So we basically just copy the dice 1. It'll appear in the same location on the stage. We're going to reposition the dice 2 by extracting data from dice 1 transformation, applying a bounding box to it, and giving dice 2 and dice, an offset from dice 1. So we want to basically put dice 2 on top of dice 1, I guess. Yeah, that's cool. Maybe let's for today let's just go over the different elements, because I think it's too late to actually implement this. Let's go over the example and then implement it next time, right? Make sense? Okay. So it's basically computing the bounding box of dice 1, getting the size, and this is how you put it like on top of each other, right? Yeah. Then we also add a little rotation around the x-axis, 90 degrees. That's how you define a rotation, right? Yeah. And then we basically clear the transformation order first, right? And then we add, here you see, right? We translate it, add another orientation, so the rotation about it, and this. You wouldn't need that actually, right? This scaling up is like we scale it with 1, so it's just the same, right? Yeah, that doesn't make sense in my opinion, but what not? Okay, so yeah, and we do the same with the dice 3, right? This is how things then turn out, right? So we have used these are the same dices, right? And so we just transformed them and rotated them, and then you can read like the USD. That's nice. And then we go like enhancing the look of our stage. Yeah. What does it do? There is like a backdrop, so it's like a scene in the back. And here we come to the lighting, yeah, and that's what I like about this book. They talk a lot about shading and lighting. So this is really nice, in my opinion, and this adds some information to the USD learning journey, right? So what do they do here? We create a distant light, right? And then we also play with the shaders. But I'd say we do this next time. You know. See, so here is how it turns out. So we change the position and also add some other colors. That's also some nice thing, right? Yeah, awesome. Here's the summary. So I'm sorry we didn't do a lot of actual programming work at this time, but I think it was good to like go over the example first, and then we go into programming next time, right? Because this understanding and manipulating X forms is important. We touched the Euler angles, the quaternions, rotation matrices. We will then, next time in the example, arrange the objects. And yeah, you can dive into the math behind it if you like. It's always good to know, geometry, math, if you're dealing with 3D graphics, right? Yeah. Next would be next time I'd say we go into the example and try to do it ourselves, right? Together. And then we also play with animation. That's also a nice thing to do here, right? Yeah, I think let's call it a day for today. I'd say if you have any, I don't think it makes sense now to start with the example. Do you have anything you'd like to ask or note or mention? So I would say, yeah, let's call it a day. You guys have a great weekend. Thanks for your time.
You
Perfect time.
too.
What?
Perfect timing for me to come in when everybody's leaving.
So Jan, your last words from Jan.
I hope you had a great time. More structured than the last meeting that we had with me. Anyway, yeah.
I was actually asking myself if you guys wanted to still cover something or like we can then see next time, I'd say. Yeah. Great. Yeah. So thank you again. I'm heading to Austria right now, and you guys have a great weekend.
Thank you.
Yeah,
Bye.
bye.
Have a great time. Bye.
Bye. Thank you.